Hello, sixth graders. Welcome to our week 8 Bellwork. This is homework that will be assigned either Monday or Tuesday and due again on Friday. If you take a look, we have a lot of review problems today. So these are things that we hope you're keeping in mind throughout the school year and kind of keeping those skills fresh. That's the idea behind our Bellwork. So taking a look at the first problem here, it says use order of operations to solve. And lots of us remember an acronym. We remember the silly saying, please excuse my dear Aunt Sally. And if you look over here to the right, I've given you some clues. So this P stands for parentheses or some type of grouping symbol. So sometimes we're going to see more like a bracket situation. The E stands for our exponent. So sometimes we have little tiny exponents of 2 or 3 next to a larger number known as the base. The multiplication and division are kind of housed together here. If you notice, that's because they work together. They really happen on the same level. So you could have multiplication first in a problem or division first in a problem. It depends on the order it's given from left to right. And last, the A for addition and the S for subtraction. But notice that they're grouped again. They put brackets around here to show you the idea that it could be subtraction first in a problem. It just depends on who comes first in order from left to right. Just like our reading. We read from left to right. I might add some arrows underneath these. I'm going to remember to go from left to right for those two situations. All right, using this kind of as our key, we're going to look over here and decide, do we have any parentheses to start? And in fact, I do see these parentheses around 24 divided by 3, so that's the first thing I need to check off. So I'm going to take care of 24 divided by 3. If you count by threes, 3, 6, 9, 12, 15, 18, 21, 24. 3 goes into 24 8 times. So we're going to get 8 from that division inside the parentheses. Those parentheses can really come off, and I always do double check to see if there's a number right next to the parentheses for some reason, but there's not in this situation. So I'm done with parentheses. And in fact, your core teacher would tell you to cross off those parentheses, show that you've already taken care of that, and bring everything else down. So we need to bring down the addition of 3 and the addition of 3 to the third power. Now I go back to my rules or my steps over here, and my key tells me to look for exponents next. Do we have any little tiny exponents telling us to maybe square or cube a number? And in fact, we do. I see an exponent of 3 sitting here, 3 to the third power. So this is the next thing we need to take care of. Well, it's really important to me that we expand this and we show what it means. Otherwise, lots of students will get the wrong answer of 9. Thanks for playing. If I were you, I would come over here off to the side and show what 3 to the third means. So this is what we're taking care of right now, 3 to the third. Well, it really means that base is going to be written 3 times. And the base meaning this big number. It's all about the base. And we need to write that base 3 times because of that little tiny exponent of 3. Now, if that were an exponent of 2, we would only be writing the base twice. And if that was an exponent of 20, we'd be writing the base 20 times. Well, it's important to me that you don't say 3, 6, 9 and get a wrong answer of 9. Sixth graders love to say that, but instead we need to take it in chunks. So we would say, what is 3 times 3? We would get 9 there and bring down the extra times 3. So we're kind of doing our own simplifying over here, almost our mini order of operations happening in this problem. So last but not least, 9 times 3 gets me 27. So I can take that 27 and I can replace the 3 to the third power in my original problem with 27. That's the same value, it's equivalent. And your core teacher would tell you to cross off the thing you've used. Well, we've used that exponent of 3 and it was sitting on the base of 3. So 3 to the third power is crossed off. We need to bring down everything else we have not used yet. So in front of the 27, I still have addition, and in front of that I still have 3, and in front of that I still have addition, and an 8 sitting out front. Well, I can check off my exponents. I definitely use those up. And next I look for multiplication or division in order from left to right. Well, going back to the problem, I'm looking for these two things. Is there multiplication or division in this problem? No. So we'll check it off and we'll move on to the next step or the next set of procedures. Next it says we're looking for addition or subtraction. In fact, we do have that, and we only have addition. So we can get ourselves really to reorder this in any way we like. But this suggests that we always move in order from left to right. That kind of cuts down on errors for sixth graders, although I do see a really nice number bond happening here with the 27 and the 3. But I'll ignore that for a moment because you've learned to go from left to right. It would be acceptable to start here and say 8 plus 3 gets us 9, 10, 11. 11. And I will bring down everything else I have not used. So I have not used the plus or the 27. And maybe just to backtrack a quick second, what did we use up? The 8 plus 3. It gave us the sum of 11. So I'm going to cross off the parts I've already used. The last thing I have, in order from left to right, well, some more additions. So we're going to go ahead and add as a last move, 11 plus 27. You could stack them up, or I could say 27 plus 10 is 37, plus one more gets me 38. So I know I'm going to get an answer, a result of 38. If you do this well and you organize your work, you're going to notice that you've just made some delicious pizza. I mean, some very organized order of operations. So it kind of looks like a pizza slice. I like to joke with my students that we're making pizza, but it's really a line-by-line organization. And I know in your classroom, your core teacher calls it a funnel. So we're funneling down each time, smaller and smaller the problem gets until we get down to one final answer. Let's move ahead here if we can. I don't know if this will let me scroll tonight or not. Looks like I might have a chance. The next thing we're looking for is a quotient. So this fancy word, find a quotient. When I look at this problem, I go, what do they mean by a quotient? Well, I notice that there's some long division happening here. So the quotient is the result of long division. So just kind of some defining here and making some good word connections with that vocabulary. Quotient means I need to divide. All right. I gave you another clue here. I used an acronym, DMSB. So dad, mom, sister, brother, some of you have learned. Does McDonald's sell burgers? Any of those acronyms might help you remember the order of steps for long division. So we're going to use that long division algorithm today, following these steps in order. So we're first going to do our division. Next, we multiply on each step. We subtract and we bring down if there's another value to bring down. Or sometimes we have to create a placeholder like a 0 to bring down and divide some more. I also gave you a clue here. Perhaps you don't have a multiplication chart in front of you and you don't remember your 11 super great. So I would always start by taking that divisor. And in this case, the divisor is that number on the outside. It is an 11. I could count by 11s. So 11 times 1 is 11. I double it for 22. I triple that for 33. 11 times 4 is 44. And I love these 11s because they have a really cool pattern to them right now, don't they? The two digits kind of look the same. 1, 1, 2, 2, 3, 3, 4, 4. That's going to continue for a while. 5, 5, 6, 6, 7, 7, 8, 8, 9, 9. Uh-oh. 10, 10 will get you in trouble. So in this case, we want to think about adding 99 plus 10 more. Well, that get me 109. Plus 1 more would get me 110. And that really relies on that zeros trick as well. When you're multiplying 11 times 10, you're going to get a 0 at the back, aren't you? And then 11 times 11, well, that would be another 11 added to this. So 110 plus 10 more is 120, plus 1 more is 121. That's probably far enough for us to go to be able to make this happen. All right, let's go ahead and get started on our steps in the algorithm. So we would say, does 11 divide into those 8,000s nicely? Can I take the 8,000s and make 11 nice groups of them? Well, it would be kind of difficult to get whole numbers. So for that reason, we would say, no, that doesn't work super nice. We're not getting a whole number there. So instead, I'm going to take the first 2 digits of my dividend, and I'm going to treat it like 83. I have 83 hundreds at this point. So could I take groups of 11? Could I make groups of 11 of those 83 hundreds? And the answer is yes. So we want to come over here and see how close we could get. Ooh, 88 is pretty close, but it goes over, so we're going to stop right about here. We're going to talk about 77. Well, we know 11 goes into 83 1, 2, 3, 4, 5, 6, 7 times. That 7 goes in my quotient. That's my answer to that division problem. And then I would multiply. 7 times 11 is 77. So we've done our division. We're multiplying now. Next step says subtract. So let's subtract these numbers. Well, I noticed that when I have 3 take away 7, it might be helpful to do some regrouping so I don't get negative numbers. So if I regroup, I would leave him with 7, and I would add 10 to the 3 that was there. 13 take away 7 gets me, well, let's see, 7 and 7 is 14. That's 1 too many, so I think 6 would work. And next, 7 take away 7 here is 0. If things are going well, you'll also be able to check and see if your leftovers are smaller than your divisor, and in this case they are. So I've subtracted. I next look to see if there's anything to bring down. In fact, there's a 7 here, so let's bring down the next digit, that's 7. Well, we say, does 11 go into 67? And it sure does. And we want to go in there nicely without going over. We're trying to get a whole number. So look here at our multiples. How close can you get me? Ooh, pretty darn close. If you notice, we can get to 66. So what did it take to get there? Well, this is times 1, times 2, times 3, times 4, times 5, times 6. Oh, 6 times. 11 goes in there 6 times nicely to get me a whole number. And 6 times 11 gets me the whole number of 66. So again, I've just done this process again where I divided 67 by 11, and then I multiplied my answer of 6 times 11 to get 66. I'm ready to subtract. When I subtract, there's no regrouping on this situation needed, so I might write it something like this. There's 1 remaining. I'm going to check to see if there's anything more to bring down, and in fact there is. Now I have 18 divided by 11. Well, how many times does 11 go into 18? If you had 18 candies, could you give me some groups of 11? You sure could, but you could really only give me 1 whole group. So I'm going to put a 1 up here in my quotient, and again I'm going to use the next step after division to multiply. 1 times 11 is 11, and when you subtract, there's something remaining. 8 take away 1. Let's see, counting backwards by 1, 7. 1 take away 1. Well, I took it all away, there's nothing left. And I could bring down those zeros if I wanted to see it, but honestly, I just have 7 remaining. Now, I know you use that crazy R word in the elementary, but I'm kind of scared of that word, I'll be honest. I like to write our leftovers as a fraction, or sometimes as a decimal when possible. So let's see if we can follow this around and think about our mixed number, our final answer. It looks like I have 761. That's the whole number. You're used to seeing that from your quotients in the elementary. But then when I come down here, there's something remaining. I have 7 little pieces out of the groups of 11 I was trying to make. So 7 extras out of the 11 needed. Final answer here would be 761 and 7/11ths. Those long divisions I know are tricky for a lot of us, so I don't want you to quit on me. I know the algorithm is a tough thing to move yourself towards, but we're starting to get there. I'm seeing it in the classroom. On this third problem, it says find the quotient. It says 2 6 is going to be divided by 2 6, and I gave you a couple hints. I said we could draw a model or we could try this reciprocal approach. And I didn't write that fancy word reciprocal. Probably should have, because it's a really important word. More likely on a test, if they're going to tell you to use a reciprocal method, then they will say freeze, change, flip, which is this shortcut, or kind of a mnemonic that we use to remember. Well, can I draw this out, 2 6? If I had 2 6 of something, a candy bar maybe. It's getting to be that season where we like candy a lot. I could split this into how many total pieces or parts? Well, I want 6 equal parts. So 1, 2, 3, 4, 5. Oops, this is a little too long, isn't it? And if I put a 6th line, you'll notice that I made it too many pieces. So I'm going to try to erase that tiny little piece at the end and see if we've got it. Does this work? 1, 2, 3, 4, 5, 6 equal parts. Perfect. But I only have 2 of them. So someone's taken a lot of your candy bar. You only have 2 little pieces to shade in or remaining. And next they tell you to divide it into 2 6. Well, this number is exactly the same. They want to see how many groups of 2 6 that I can make. Well, if you notice, it's going to take 2 of these 6 to make 1 group. I'm only going to get 1 group. The answer really is 1. This makes good sense to me for another reason, and we could check it with a reciprocal if we like, but whenever I have a number and I divide it by itself, well, it goes in there a whole or 1 whole time, doesn't it? So whether I have 5 divided by 5 or 2,000 divided by 2,000, I'm always going to get 1 back when I divide a number by itself. So there's kind of some patterning that helps me with that also. Now some of you are like, what do you mean by reciprocal? Freeze, change, flip. Well, if you've learned the reciprocal method, you would take the first fraction and keep it the same. We keep the 2 6 the way it's given. But in a reciprocal method, we multiply by the reciprocal, or we change from division to its opposite, multiplication. And the last thing we would do is this F or the flip, or we might say reciprocal, where it really, if I were to multiply by this number, the definition of a reciprocal is that you'll get 1 back as a result. Is that really true? Let's see if it works out. Some of you might see some cross simplifying here, but let's just multiply across and see what happens. 2 times 6 would get me 12 in my numerator, and 6 times 2 would get me 12 in my denominator. 12 twelfths. That looks like a different answer. Or is it? Hopefully you recognize that if I had all 12 pieces of the 12 that I started with, I would have 1 whole. So it's another way of showing 1 whole. It does check out. All right, this next problem is kind of using something similar. It says we need to come up with a division problem. So they give us a model. What division problem is being modeled? Well, if I look over here, what fraction do you see first? So this first fraction, I notice that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 little parts. Okay, so that's going to be my denominator. But how many are shaded? 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. I'm starting with 9/12. So that could be my first fraction, 9/12. And I'm trying to split it into whatever the second bar shows me. So it looks like I'm trying to split it into some number of 8s. Are there really 8 parts? 2, 4, 6, 8. Sure are. That's my denominator, isn't it? But how many are shaded? 1, 2, 3, 4, 5, 6 of them. 6 8s. I'm really going to say, what is 9/12 divided by 6 8s? I'm trying to use this comparison bar model to come up with a division problem. And it looks to me like I should get an answer of 1 whole. And I say that because I notice that the length of this bar in the shaded region is exactly the same as the shaded region in the second bar. They're exactly the same. This 9/12 is equivalent to 6 8s in the bar model. So I should get 1 whole as an answer. You might say, how's that possible? Well, I noticed that 9/12 could be simplified. 9 and 12 both divide by a common factor. What factor goes into both 9 and 12? You can check your multiplication chart, see if you can find them in the same row. Maybe you'd notice they're not even, but they do both divide by 3. 3 goes into 9 3 times, and 3 goes into 12 4 times. 9/12 is equivalent to 3/4. We'll take a look at the 6 8s. Both those numbers are even. What if I tried to simplify this fraction? Would you notice anything? 2 goes into 6 3 times, and 2 goes into 8 4 times. Do you notice that I have 3/4 divided by 3/4? Isn't that similar to the last problem where I had a number divided by itself gets me 1 all the time? There's another way of checking that. It does check out. The next problem is another long division problem, and I would love to say that students would be able to use my last example to get themselves started, but I know how tough these are for us right now. So for that reason, I'm going to try to zip through it and hope that you're doing okay to follow along. So quotient, what did we say it meant? Long division. We're going to find a answer to some sort of division problem. And over here I see a long division setup, is why I said that, long division for this one. And notice I also gave you a hint. You need to know your multiples of 18. Well, good thing we give you really huge charts, but let's pretend that you're taking some state test. Hint, hint, wink, wink. And on the state test, they might not give you all the multiples of 18. You'll have to figure them out. So 18 times 1, well, we know will be 18. But if I had to figure out 18 times 2 off to the side, I could actually do the multiplication and see what I get. Or I could check my chart if I'm allowed to use it, and I'd get an answer of 36. I could do the same thing each time. Someone else I've seen do this on their paper, where they add 18 each time. And then they take that result and they add 18 more. So there's another way of going about that. Yeah, you add each time you add 18. Now I'm thinking of it differently. I'm thinking I could add 20 and take away 2. Because isn't 18 like 20, take away 2? So let's see if that would work. What's 54 plus 20? Oh, well that'd be 2 10s plus 5 10s is 7 10s. 7 10s and 4 1s, 74. But I have to remember to take away 2 when I'm done. So 74, count backwards, 73, 72. All right, let's try it again. What if I add 20? Well, that 20 and that 70 are going to line up, aren't they? So 2 10s plus 7 10s gets me 9 10s. 9 10s and 2 1s, 92. But don't forget to take 2 away from it. 92, take away 2. Yeah, it's 91, 90. And I could do this again. I could add 20 another time. I could say, well, 2 10s plus 9 10s gets me 11 10s. And there are no 1s at this point. So I'd have 11 10s or 110. But don't forget to take 2 away from it. So 110 take away 2. Well, that'd be 109, 108, 108. And I can continue this pattern if I needed to, but hopefully I've gone far enough to make this work. So even though there are more lines, I can always return to this later if I need to. Let's go ahead and try this strategy where we say, does McDonald's sell burgers? Sometimes we say, does McDonald's serve cheeseburgers? So that you remember to do that checking step. First move, we need to divide. So I take the first digit, the largest place value. It's a 9 in the thousands place. I have 9 thousands. Can I split that into 18 thousands? Well, not to get a whole number, right? I'd end up getting a fraction or a decimal. So oftentimes we'll say, no, we'll put a 0 here. And for our purposes today, we'll say, no, I can't split that into nice whole groups. So next, I take the second place value. I treat this as 98 hundredths. So, or 9,800, I guess I could say that also. And I want to see how many times 18 will go into that. into the 9800s. So I have 98 to work with. I want to look over here and see how close I can get without going over. Oh, I found it. I think that I could say 18 goes into 98. It will get me really close. It'll get me to 90. But how many times was that? Well, this is times 1, 2, 3, 4, 5, times 5. So, oops, that's not a very nice looking 5 for my video or for my students. So we'll try that again. 5. So what that means is 18 goes into 98 5 times nicely, and 5 times 18 gets me 90. When I subtract, I'm left with 8, and 9 take away 9 is 0. You want to check to see if things are going well. 8 is smaller than your divisor. So next we will bring down the next place value. I have 87, and I want to try the same strategy again. I have 87 tens in this case, and I'm trying to make groups of 18. So how many groups can I make? Well, here I'd count up as close as I can to get to 87 without going over. Oops, 90 is too much, so let's try this one. 72. Well, how many times was that? 18 times 1, 2, 3, 4. A 4 goes in your quotient. And 4 times 18 is actually 72, we said. And we're ready to subtract. 7 take away 2 gets me 5 in the ones place here. 8 take away 7 gets me 1 in the tens place here. And actually, if I consider my place value, I've kind of mathematically lied to you. I didn't mean to do that. But I get 5 and 1 here. And 0 take away nothing, 0. And this is why I say that place value is a little bit off, because I have another place value to bring down. And technically, I have 156 to divide by 18. And I'm in trouble because I noticed that I stopped at 108 over here. So we have to go back to our strategy of counting by 18s again. So I'm going to add another 20 and take away 2. Well, 128 take away 2 is 126. That's pretty close. I'm going to try it again. I'm going to add 20 and take away 2. 126 plus 20 is 146. Take away 2. Oops, that's 144. And I'm going to try again because maybe I can get a little bit closer. I can see my lines are too short here, but I'll keep going. I'll add 20 to 144, so 144 plus 20, well, that's going to change the tens place to 164. Take away 2, 163, 162. I'm going to get 162. Oh, this one went over, didn't it? I'm trying to get as close as I can to 156 without going over too big, so let's stop here. This 144 is going to be useful in a minute, but how many times did we say 18 went into that nicely? Well, let's try. 1, 2, 3, 4, 5, 6, 7, 8 times. 8 goes in my quotient. 18 divides into 156 8 times nicely to get me a whole number. And 8 times 18 better get me this 144. And that checks out in my head because I know 8 times 8 is 64. And 8 times 1 is 80. When I add those together, this will work. 6 take away 4 is 2. And 5 take away 4 is 1. 1 take away 1 here in the hundreds place is 0. And that 0, if you want to see it, you could. This is really close to a final answer, but I notice there's nothing more to bring down. So for today's purposes, we've been practicing writing these as mixed numbers. Notice with no more digits or place values to bring down, I could put a decimal point and some zeros back here and go to decimal land, but we really could call this our answer in mixed number form. So let's write our whole number from the quotient, 548 whole groups. But I had 12 little pieces left over out of the 18 I needed. Oh, this isn't bad. In fact, your teacher would probably be pretty impressed if you got it. But I gotta be honest with you, this is not a final answer. Can you believe there's one more move on this crazy division problem? Look at this fraction. What could you do with the 12 and the 18? Do you see that we could simplify it? So when you can simplify, do simplify. It's kind of like shop till you drop, do the math till you drop. No, I don't want you to drop doing math, but I do want you to keep simplifying when you can. So in this case, what goes into 12 and 18 nicely? Well, they're both even, so 2 might work. 4 goes into 12, but not nicely into 18. Oh, 3 goes into 12 and 18. Oh, but if 2 and 3 both go into both numbers, 6 should also be a factor. And in fact, it is. So let's go ahead and simplify this a little bit. I'm still going to have 548 as my whole number, but 6 goes into 12 twice, and 6 goes into 18 3 times. 6, 12, 18. I have a simplified answer, final answer, 548 and 2/3. It was probably worth looking at that long division problem because there is some simplifying that we haven't seen in a while, huh? For this next problem, they're asking us to multiply some decimals, and I know this video is getting long, so if you need to take a break, I would encourage you to break this into chunks, into multiple days. But it says, find the product. That means I'm going to use some multiplication, And this decimal multiplication is something we haven't seen yet. We're going to introduce you to that in Chapter 3 of Math and Focus, I believe. So I give you a hint. I say let's stack the numbers, then count the total number of decimal places for your answer. So we're just going to stack the numbers. And that does not say stack the decimals. If you notice, it says don't worry about that. It kind of says that. And this is really tough for students because they're so used to hearing stack the decimals, stack the decimals. It's true, you need to stack those place values when you are talking about addition and subtraction of decimals. But when we're multiplying or dividing, we do something a little bit different here. So I'm going to show you multiplication off to the side. Well, this doesn't say do anything with the decimals at the moment. In fact, sometimes we say build a decimal bank, but I'm going to save that. I'm going to tell you to hold off a minute. Let's go ahead and do our multi-digit multiplication and ignore the decimal for a quick moment. So let's try that. 1 times 2 is 2. 1 times 30 is 30, or 3 tens. 1 times 2, oh gosh, I got my place values off again because we're talking decimals. So 1 times 200, 2 hundredths is 2 hundredths. 1 times 3 tenths is 3 tenths. 1 times 2 ones is 2 ones. 1 times 3 tens is 3 tens. And I'm ready to move over. If you remember with our place value rules, when I'm moving over a place value, those are always jumps of 10, aren't they? So I'm going to cross off my 1 and show you that I'm moving over a hop, and I'm saving this place with my friend Bob, or a placeholder of 0. Well, now I have 2 times 2, which gets me 4, and in a moment we'll see that that's actually 2 groups of 2, well, let me say this right, 2 groups of 2 hundredths should get me 4 hundredths in a moment. Now I have 2 times 3, which should get me 6 using the algorithm. 2 times 2 should get me 4. Moving to the next place value, 2 times 3 up front would get me 6. And what do I do after I've done these partial products? I add them together. So 2 plus 0 gets me 2. 4 plus 3 gets me 7. 6 and 2, 7, 8, gets me 8. 4 plus 3 gets me 7. And 6 plus nothing, some people like to show a placeholder here, gets me 6. And this number is way too big. It's huge. This is saying you have 32 times something close to 2. If I were to use some estimation skills, I know this is way too huge. So now we go back and we talk about that decimal placement. So I said, count the total number of decimal places for your answer. Your core teacher is going to call this the decimal bank. She's going to tell you to look for how many places are behind the decimal of the first number. Well, this is 1, 2 hops. So there are 2 decimal places to save. And look at the second number. There's 1 decimal behind, no, 1 place value behind the decimal. So I'm going to save 1 place in the bank. If I total those up, I'm really saving 3 places. This is another way of saying it. I've divided this number by 10 twice. When you divide a number by 10 once and then another time, you've really divided by 100. And I've divided this number by 10 one time. So when I divide by 10 1, 2, 3 times, I'm really dividing by 1,000, or 3 zeros is what I'm thinking about. I want to write this to the thousands place. So we start at the back and we make those 3 hops towards the front. 1, 2, 3. And I'm going to end up with a result of 67 and 872 thousandths, tenths, hundredths, thousandths. And that's perfect because I wanted to divide by 1, 2, 3 zeros, or 3 place values, and that's going to be the same as dividing by 1,000 or turning it into thousandths. This is a final answer. That's really tough. Again, you haven't seen that yet this year. It's possible that your core teacher is going to change this problem without me knowing it. I'm just trying to video this ahead of time, so hopefully yours looks something like mine. If not, we'll just change it over a little bit. This next problem is similar, where it says find the quotient. We're working with decimals this time though. So we're really going to use the same strategy we've been using in long division, but we're going to use it with a decimal. So let's see if I can write this out for you. The first number I'm given becomes my dividend, 802 and 4 tenths. The second number I'm given is the number of groups I'm trying to make, or the number of pieces I'm trying to put in each group, I guess. If you notice, it says rewrite as long division. Check. Move the decimal behind the divisor blank hops. Well, how many hops would it take, or moves would it make, if the decimal were to move behind this number to make the divisor a whole number? Well, it really would move 1 hop. You really multiplied that by 10. If I do that to the outside, I need to do that to the inside. I need to multiply the inside number by 10 also. So in this case, 1 hop, doesn't have an S on it. I'm going to repeat with the, I think that says dividend back there, but it got chopped off. So that's what I'm showing you. I sometimes call this Simon Says. The number on the outside is Simon, and he's telling you to hop once to the right. Well, if you want to win the game of Simon Says, you better do it. Hop once to the right, and this is the location of my new decimal. Okay. I would probably just do a rewrite at this point to see if we can clean this up a little bit. So I'm going to treat this like a whole number of 17, and it's going into 8,024. We could again use our does McDonald's sell burgers, and we also could use our idea of multiples, which came from your first unit of study, to make sure that we can get as close as possible. So counting by 17s here, 17, 34, and then I have to think, oh my gosh, it's like adding 20 and taking away 3. So 54, take away 3, 51, add 20, 71, take away 3, 70, 69, 68, add 20, take away 3, 68 plus 20 is 88, take away 3, should be 85, add 20, take away 3, 85 plus 20 is 105, take away 3, 102, and I might have to come back to this. I kind of hope I don't have to, because those are tough in my head right now, this time of night, but I may have to return to that in a little bit. All right, let's go ahead and try our strategies. So using our algorithm, the 17 go nicely into the 8,000s, meaning could I make 17 separate groups and put thousands in each? Well, not unless I wanted to break those thousands into pieces, right? So for that reason, I put a 0 in my quotient. And I'm going to then treat this like 80. So I'm taking those 8,000s and I'm breaking them into instead hundreds. Is kind of what I'm doing. So I have 80 hundreds to work with, and I'm trying to figure out how many hundreds would land in 17 different groups. So let's get as close as we can to 80 without going over. I see it here. So 68 is going to go in my subtraction in a moment. And I have to figure out what number to put my quotient. So 17 times 1, 2, 3, 4. 4 goes in our quotient here. That means 17 goes into 84 times nicely. 4 times 17 is 68, and I'm ready to subtract. There is a little regrouping here, if you noticed. 10 take away 8 gets me 2, and 7 take away 6 gets me 1 out here in the thousands place. So I still have 1,000 to work with. I still have 200s to work with. And if you notice, I have some other place values to bring down. So I'll bring down the next placeholder, that 2, and we're ready to divide again. Does 17 go into 122? It does. And darn it all, I stopped counting over here at 102. So let's get back to it. I'm going to add 20 and subtract 3. Well, that'd be 122 minus 3. Well, take away 2, I'd be at 120. Take away 1 more, sounds like 119. That's darn close, isn't it? I better try again, though. Add 20 to this, I'd have 139. Take away 3, I'd have 136. You may want to check your multiplication chart and make sure I'm not going crazy here, but I think we're close. So 119 looks like it's going to work for me. Assuming that I've done my math correctly, mental math here. I'm going to use that 119 in my subtraction. And I need to keep track of how many times 17 went into 122, or how many groups I was able to make. So let's count over times 1, 2, 3, 4, 5, 6, 7. I'm going to put a 7 up here in my quotient, and 7 times 17 should get me that 119 that I already wrote. I'm ready for some subtracting, but 2 take away 9 would get me a negative, so I oftentimes will do a regroup instead. I'll change this to a 1, and that group of 10 that he just gave me adds to the 2 that was there. 12, 10 plus 2 is 12. Next, I take the 12, take away the 9 from it, and counting backwards, or counting up maybe from 9, 10, 11, 12, I'll have 3 remaining. 1 take away 1, well, taking away everything you have, it leaves you with 0 in both those situations. We're not quite done yet. I notice that there's another place value to bring down. So I have 34 here, and it's going to be divided again. So every single time there's another digit to bring down, you get to drive through the drive-thru again. Does McDonald's sell burgers? Yes, they do. So you can also do long division. Take a look. Does 17 go into 34? And if so, how many times? Well, actually, it goes in perfectly, doesn't it? It will actually get me directly to 34. So how many times is that? 17 times 1, 2. A 2 goes in my quotient, and 2 times 17 is 34. And when you subtract, there's nothing remaining. Things are looking pretty awesome. On our previous long division problems today, we ended up with something remaining, or a fractional answer, mixed number. We don't have that this time, and we don't have a decimal either. We could have, but we but we didn't get a decimal. We ended up with a whole number result. 472 is the final answer. All right, just a couple more to go, and we're trying to zoom along. And again, this is way too much math for some of you to do in one sitting, so go take a break, stretch your legs, do some jumping jacks, and let's take a look at the next problem when you're ready. Next it says, Cassie has 8 red marbles and 12 yellow marbles. Her mom doubles her red and yellow marbles for her birthday. I think it probably says back there, use the distributive property to show how many marbles Cassie has. And I'm sorry that my scrolling is kind of crazy. I made this really big, and it's hard for me to see all the details, but I think it's darn close. It's close enough for me to get the idea. So I have 8 red marbles. That's pretty important, isn't it? And I also have 12 yellow marbles. I could maybe even get out my yellow highlighter here, highlight the yellow for you. And it says that she doubles them. What does it mean to double something? Oh my gosh, I'm going to double the number of problems you have to do tonight. Oh my gosh, I'm going to double your score. Oh my gosh, you get double the cookies that you had yesterday. What does it mean to double? Hopefully you're thinking to yourself, I know that means to take the number and add it to itself. Or maybe some people would say times 2, multiply something times 2. So let's talk about that. If I keep track of my red marbles and I keep track of my yellow marbles, right now I have red, which is 8, and yellow, which is 12. What if I were to double them? If I doubled this, that would mean I'd take the 8 times 2. And if I doubled that, I would take the 12 times 2. What would I end up with? Well, 8 times 2, well, 2, 4, 6, 8, 10, 12, 14, 16. I would get 16 red marbles. What if I took 12 times 2? Well, counting by 2's again, or maybe you know your multiples of 12, 12, 24. I'll get 24 yellow marbles. An upcoming unit that involves ratio is going to show you how to organize it something like this. We would write red to yellow. So kind of thinking ahead, we use this colon to show a comparison. And we would write the 8 to 12. And this is called an equivalent ratio, when I can do the same thing to both sides of my ratio. I could multiply both sides by the same factor, or I could divide by the same factor. And when I decide to do that, I'll end up with an equivalent ratio. So again, I'd multiply both sides by 2. There's another way of just showing your work along the way. This is called ratio. And I know it looks like radio, but this is ratio. Food for thought. We're moving there soon. All right, I think this might be our last problem for our Bellwork week 8. So lots to look at today. Some of these things are relatively new. So thank you for sticking it out and trying some new strategies today. This last one says, Ms. Smith has 28 6th graders and 35 7th graders. If she wants to break the 2 grades into identical groups without any students left over, how many students should be in a group? Oh, this reminds me of a field trip. If I was taking these 28 6th graders and 35 7th graders on a field trip, I don't want to leave anyone behind. And I want my groups to be the same size, so one parent doesn't say, that's not fair. You have fewer students than I have. I want it to be the same. So I like this piece that says, into identical groups. I gave you a hint. If I'm trying to break things into identical groups, I have to find something that they have in common, right? I have to find a factor that will work for all of them. So I said, think factored form. We did that in chapter 1. And find the GCF first. Oh, GCF, greatest common factor. So I'm really going to divide these into their greatest common factor. I'm trying to find what they both share. Well, you've learned how to do this a couple of ways. T-charts, trees, ladders. But I'm going to try today trees because I see most students seem to prefer this idea. 28 and 35. They're both composite numbers. I was going to say compound. They're both composite numbers. So we can break them down. We're going to try to get them to prime numbers soon. So 28 is the same as a fact that we know, 4 times 7. Check your charts. Is 4 prime? Is 7 prime? You should see that 7 is prime, so we'll circle it. 4 can be broken down. It's the same as 2 times 2. So I'm trying to break it down to the smallest possible factors that are prime. And 2's are prime, so I circled them here. 35, well, it ends in a 5. Big clue to me, I could divide this by 5. 5 would be a factor of it. 5 times what? 5, 10, 15, 20, 25, 30, 35. I think that was 7 times. So I check my chart. I say, is 5 prime or composite? In fact, it's 5. It's prime. And 7, I'd say, is it prime or composite? And you would again say it's prime. It's getting a little late in the night for my video. I'm sorry for all my errors. All right. Next, with all good trees, you should chop them down. Okay, that sounds harsh. Sometimes we laugh about that, but it helps us remember to organize our prime factorizations. So 28 is the same as, just the prime numbers, remember? I'm going to put them in order from least to greatest. 2 times 2 times 7. 2 times 2 times 7. And for 35, I'm going to record it as, again, just its prime factorization. Actually, I only have 2 prime numbers on that tree. 5 times 7. So my question to you is, do you remember how to find the greatest common factor after doing all these steps? We made our trees, we chopped them down, we organized our factorizations. Now we look for something they have in common. I'm trying to make groups that are in common, the same number of 6th graders and 7th graders, so they look alike. Well, I notice that both of these groups have 7. Is there anything else that they both have in common? Be careful, don't choose those 2s. Why not? Oh, those 2s belong to the 28 only. There's not a 2 as a factor of 35. This 7 actually becomes my greatest common factor. That means that I can make 7 equal groups. Oh, or 7 groups. That's super helpful, and I gave you a hint down here. I'm trying to figure out how many identical groups to make. 7 it is. So the question is, how many 6th graders does each group get? How many 7th graders does each group get? Well, taking a look here, I could really look at my extra factors. Or I could say, how many times does 7 go into 28? 7, 14, 21, 28 goes into 4 times. You're going to get yourself 4 6th graders each time, or in each group. Next, I'd say, how many times does 7 go into 35? And you might say, oh, it goes in there 5 times. So I'm going to get 5 7th graders in each group. This really is a final answer. I'm going to show you another spot where you could also see those answers. Look around at your prime factorization. Do you see where we wrote out 28's prime factors and 35 as a product of its prime factors? Well, what do you notice is remaining in 28? A 2 and 2, right? What is 2 times 2? Aha, it's 4. How about in 35? What wasn't in common? Oh, that 5 wasn't in common. We ended up with 5 7th graders in each group. This really is the final answer. This is the factored form that they're looking for. There might be a better word answer, like I might be able to say Miss Smith is going to make 7 groups with 4 6th graders and 5 7th graders in each, and that might really impress your core teacher as well. All right, thanks for sticking with me for so much bell work this week. Hopefully you learned something new or reviewed something that maybe you had forgotten, and you're turning in something with some excellent quality the next time I see you.